minus t d2 sigma Polyakov Lagrangian. This is minus 2 by 2 square root of minus g times h alpha beta g alpha beta, and if this is h alpha beta, this is delta alpha alpha, and this is equal to 2. So this is then equal to 2. This is just t minus t square root of minus h, and this is so you again recover the Namakov action. So this is just to tell you that classically these two actions, Polyakov action and the Namakov action, they are both classically equivalent. Now we let me first before I go to the symmetries, let me first prove what I have just said. Okay. So let me consider the Polyakov action minus t by 2 d2 sigma square root of minus h, and then or this, let me just call it h dot g, and now let me vary the variational let us make use of the variational principle to this. So what you have is delta s is minus t by 2 d2 sigma into square root of minus this plus and here let me write h dot g. Okay, and as you have in gravity theory, this delta of without its derivation, let me just write its value, minus 1/2 square root of minus h alpha beta delta h. Just what you do in general relativity, a delta of the square root of minus g. Right? In gravity theory, you very often need this. Okay, and this is minus 1/2 square root of minus g alpha beta delta g alpha beta. Okay, just from general relativity, without going into the details, I use this expression, and then you put both of them there, and then So I have minus t by 2. I can make one step, cut on one step. So d2 sigma square root of minus h delta h alpha beta. I take common, then this is gone, this is gone, this is gone, this is gone. So I have here g alpha beta from here. Now from here I have, this is gone, this is gone, this is also gone, this is also gone. So I have just minus. Am I missing one point here? H on this is okay. H alpha beta is here. Please just check that I have not made any mistake. This from here, this is gone here. Delta H alpha beta is gone here. H alpha beta comes here, and H dot G comes here. Okay. What about this factor of minus 1/2? Oh, there is an extra factor of minus 1/2 here. There was one, this is minus t by 2, there is one extra minus 1/2 here. So this is correct. Okay? Because it is going to be used at many places in the future, the definition of T alpha beta. And from here, we now define or construct this to be equal to T alpha beta. Okay? Let us call this object as T alpha beta inside the rectangular bracket. And then what you have is d2 sigma T alpha beta, where T alpha beta is your,
Okay, so you define this to be T alpha beta.
This I defined as
Not T alpha beta.
Sorry, thank you. Huge mistake. You can do that, yes. It's very easy to make blunders in life, yes. Okay, so this is T alpha beta, all right? And at many places you will find this as the defining defining thing, that delta S is delta S delta H alpha beta, delta H alpha beta, keeping delta H mu fixed, keeping delta X mu as 0, so keeping other variations as fixed, this, and this H equal to minus T by 2 d2 sigma square root of minus H T alpha beta, or in some literature you might find this as the definition for T alpha beta. What actually happens, this energy momentum tensor T alpha beta, it measures the response of S with respect to the metric variation delta H alpha beta, keeping all other fields unchanged. So this is one of the standard definitions that you find at many places. So I repeat, then the T alpha beta measures the response of S to the metric variation with respect to the metric H alpha beta, or that delta H alpha beta, keeping all other fields fixed, which means delta X is equal to 0. And this is what you exactly obtain here. You see what you have done here. You have varied the action with respect to what does it mean? It means you have assumed that the variation with respect to X mu is 0. Okay? Without saying that, if I write it like this, otherwise I should also vary. I should also vary it with respect to X mu, but assuming that delta X mu is 0, so I keep X mu fixed, and therefore, but anyway, all these things are self-consistent. Okay? They are all self-consistent. Now we could go a little bit further. Yes, so I think I could remove all this. And when I give you the connection of the light front coordinates with the incident form coordinates, including that of the metric, I have in my mind to tell you a few calculational simple steps, which are usually not written there in the literature, but without them it becomes difficult to proceed further, and with them it becomes much easier to proceed further. So there is one of the, I'll talk about the symmetries, and one of them is this bisymmetry. You see, in the we can have symmetries with respect to the target space or the space time, and we can have symmetries with respect to the worldsheet space. So this is one of the symmetries which is with respect to the worldsheet coordinates sigma and tau. And here H alpha beta, of course it's a function of sigma and tau. It goes at H prime of alpha and beta, sigma and tau, and this is e to the power minus 2 omega sigma and tau, or sigma H alpha beta tau and sigma. This could be e to the power minus 2 omega, could be expanded as 1 minus 2 omega plus into H alpha beta. This could be written as H alpha beta plus delta H alpha beta. Here this delta H alpha beta is minus 2 omega H alpha beta. So then we have to watch out with respect to the indices being upstairs or downstairs. When it is this, then it is the inverse of that, and this will give you plus now. You see, as usual in all transformations, if you express the transformation in this form, this is called as the finite form of the transformation. Right? This is called as the finite form of the transformation, and this is called as it is the same transformation but expressed in terms of the infinitesimal quantity. So this is called as infinitesimal transformation. Okay? So you can write, I mean, just by expanding it and collecting the things here. So this is in the infinitesimal form, and one is in the so this is with h alpha, I mean h alpha beta going to h alpha beta plus delta h alpha beta. This would be infinitesimal form. Infinitesimal form of transformation, and h alpha beta going to e to the power minus sigma times, this is called as the finite form of transformation. Okay, these are just two different forms of transformations, this or this. Now in the same go, I wanted to prove one thing, for which I directly jump onto the word sheet symmetries. It was mainly to prove that T alpha beta was equal to 0. So what was delta S now minus d2 sigma square root of minus h into, now this is T alpha beta Now I put the value of this delta H alpha beta, which is minus 2 omega of sigma H alpha beta into T alpha beta. Fine. I have just put the value of this delta H from the infinitesimal form of transformation that we just wrote down. Okay. And if now let us see that this is non-zero, this is non-zero. According to the variational principle, I should have 0 equal to delta S, and therefore all this ought to vanish, and this is possible only and only if T alpha beta is 0. So only if T alpha beta is 0, right? Okay, and so T alpha beta should therefore be 0. Although we can calculate its components T00, T11, T01, T10. Okay. Or similarly, in the light front, we could calculate T plus plus, T plus minus, T minus minus, T minus minus. Okay. If we write it as a 2 by 2 matrix. Okay. Then, but overall T alpha beta has to be 0, which means each of its components has to be 0. Each of its components will have to be 0. This actually gives rise to the so-called Virasoro constraints. Eugenia wanted to know Virasoro constraints. So when you have all the components of T alpha beta to be 0, they would be some of them would be naturally 0, but some of them may not be 0. There would be some expressions like del minus x mu whole square or del plus x mu whole square, something. Then they are the so-called classical Virasoro constraints, and they actually become very useful because when you consider the mass spectrum, which means you consider the Fourier modes for this x mu as well as for psi mu, and then these components of T alpha beta equated to 0, which give rise to the, without giving mathematical expressions, they give you some conditions, constraints, which are Virasoro constraints. Then they get converted into the Virasoro constraints expressed in terms of the annihilation and creation operators. So they are operators, so you call them quantum Virasoro constraints. Okay. And what happens here? We have some expression for T alpha beta, because all this that we considered so far today was on bosonic string theory. Okay. And we have arrived at certain expression for T alpha beta. We have not yet written down explicitly its various components, which we can do, because once we know its definition, what is T alpha beta, then we can always write down its values, T00, T01, etc., or T plus plus, T plus minus, etc. But they individually need to be, because this is a general proof that here all these things are non-zero, so the only guy that can vanish is T alpha beta. This is the only guy that can vanish. So T alpha beta has to vanish. Okay. And now this is a purely bosonic string theory, but one can arrive at similar conditions on T alpha beta when you have the, if you add the fermionic degrees of freedom into your action, like you would do in the R and S superstrings, then the T alpha beta would pick up additional terms. Not only this, but additional terms. Okay, which would arise because of the presence of the fermionic coordinates. Okay, fermionic variable psi of mu. Okay, so then accordingly, so the Virasoro constraints would change at the classical level. At the same time, when you will go to the Fourier modes, expansion of the psi of mu, and we will see here. I had thought I would go all the way up to that today, but perhaps we cannot. So this is one, and similarly, I have forgotten. Anyway, you will have Dirac equations, okay? You will have Dirac equations, and then you will have Fourier modes here. This would be Klein-Gordon equation. You will have Fourier modes there. You will decompose this x mu into the annihilation creation operators. Here you will again expand it into the annihilation creation operators. But we would now remember that we will make use of those without giving you the explicit algebraic expression for the components of T alpha beta. But once we know its definition, we can write down its components. Okay. So they would be the classical Virasoro constraints, and then you will get the corresponding quantum Virasoro constraints. And they would be crucial for obtaining the mass spectrum of the theory. And they would also be crucial for fixing up the number of critical dimensions. In bosonic string theory, it will come out to be 26 because of that. In fermionic, superstring theory, it will come out to be T equal to 10 for the same regions. Okay. So this is next time we would need also here you could prove that T alpha beta is crassless. Trace, this would be H alpha beta, T alpha beta, this would be T alpha alpha, and this is the trace of T alpha beta, and this could be proved to be equal to 0. We have only a couple of minutes left, so let me Symmetries we will do next time, but we could make use of their result. Okay, like just to mention you. That the Polyakov action would be seen, we will do it next time, that it will have 3 worldsheet symmetries. 2 arising because of the reparameterization invariance of the theory, and 1 arising out of the Weil invariance of the theory. So that means we will have 3 different gauge parameters into our theory, with respect to which the theory would be invariant. Okay, and we will make use of some of those degrees of freedom, the gauge symmetries of the theory, to fix up H alpha beta. So you see, in the first place it has to have a Lorentzian signature, so this would be equal to plus minus of that because of the Lorentzian signature. Okay, this is one condition, which is not because of the gauge symmetry. It is just because of the Lorentzian signature. It has to have, if I set it equal to 1, then if this has to be minus 1, then this has to be plus 1. If this has to be plus 1, then this has to be minus 1. So the Lorentzian signature of space and time. And if I set this equal to 0, this equal to 0, then I could set minus 1, 0. Then this by symmetry H01 would be equal to H10 by symmetry, because H alpha beta or H alpha beta is a symmetric two tensor on the worldsheet. It's a symmetric two tensor on the worldsheet. So by symmetry, this has to be equal to this. And because of the Lorentzian signature, this has to be plus or minus of this. And I just can set this equal to 0, then this becomes 0. I set this equal to minus 1, then this becomes plus 1. So apparently I can take H alpha beta to be this, and in fact it's not like this, it is actually H of, and this guy is taken as 1. So we will talk about it next time, and then this is because of the conformal invariance. Okay, so out of these 3 gauge symmetries we make use of some of them to fix up this H alpha beta, and we leave some scope which is called as the residual gauge symmetry, that we can make use of later at some later point of time. So if you like I can stop here. What we need to do further is we need to understand the symmetries of the Polyakov action, symmetries with respect to the words, with respect to the space-time manifold, which means with respect to the target space, and symmetries with respect to the words, which is reparameterization invariance 2 and Weil invariance 1. Okay, these 3. And this we may not go into too many details, but we need to recap the concepts, and then the variation of the action we would consider, which would give us the term corresponding to D'Alembert x mu equal to 0 plus boundary terms, and we have to, this boundary terms we would consider because they would define different kinds of theories, Dirichlet boundary conditions or Neumann boundary conditions, or at one end, so MN or DD or DN or ND, 4 combinations. So this and then we are ready to consider all those things with the fermionic part of the superstructure. Okay, so that's our goal. This is how we go to try to understand these things. So if you like, we can conclude our day here, and let me thank you all very much. Thank you very much.